Hello everybody and welcome back to the Damage Control Assistant Senior Enlisted Curriculum of the United States Navy and United States Coast Guard. This is the fourth installment. I'm Lieutenant Timothy Mueller, the instructor, and I'll be going over ship nomenclature today. When it comes to ship nomenclature, especially when ship stability is concerned, it is crucial that everybody on board, whether it's engineers, operators, people in combat, completely understand everything that's being talked about when it comes to nomenclature and shifting weights. If the DCA orders weight to be shifted from one place to another, and the person receiving that message doesn't interpret it correctly as the DCA is already calculated, you could have a catastrophic failure in ship stability wise, and no one knows exactly why. So in this lesson, on the left side of the screen, we're going to have all the terms that I'm going to be defining. This will be changing throughout the video as I have a little bit more than 12 terms to go through. On the right side of the screen, we have a diagram on which I'm going to demonstrate these terms. This is the transverse view of the ship. So on each side of the center line, we're going to assume that the hull is mirrored. So this is going to be our starboard side. Port side would be perfectly mirrored on the center line. However, we know that there are certain vessels such as flat decks, amphibious, aircraft carriers, and the like who have special operations where they can't necessarily be perfectly mirrored. So the first term we're going to go over is camber. Camber here is the curvature of the decks. You will always have ships that are higher in the middle on the center line than they are all the way at the very corners. This allows for drainage as well as structural stability that's provided by the decks themselves. Next up is the center line. The center line of the ship runs all the way from stem to stern and just dissects the boat perfectly in half. The symbol that we'll be using from now on is this. It's a C with an L that starts in the middle of that C. And you can see center line runs all the way from the top down to what we'll find as the keel. Next up, we have design waterline, or as it's also called as designer's waterline. This is the place where the hull is designed to have an initial waterline, as the name suggests. When you develop ships and develop hulls, you have to have one certain condition for the hull in order to do all your calculations around, because as you can probably think, every hull has an infinite number of different conditions it can be, where its center of gravity is, different weights and displacements. So if you just have one that you design off of, you can start making corrections off of what that initial condition is to get as close as possible to your current condition. So number 3 here is the designer's waterline. However, we know that the waterline isn't going to stay constant there. As the ship gets heavier, the waterline is going to go up. Similarly, as it gets lighter, it's going to go down. So any plane here that's parallel to the design waterline is just called a waterline. Next on the list is freeboard. Freeboard is something that goes hand in hand with what's called reserve buoyancy. Freeboard is located right here. So it goes between the design waterline and then the deck edge. This point D is the edge of the deck, or the deck edge. Freeboard is the amount of hull that's able to sink or actually go into the water because it can roll, and this point can come closer to the waterline. So that's how far the deck can roll or be immersed without water actually coming up onto the deck edge. All right, now number 5 on the list is something that everyone that served on a ship should be pretty familiar with right now, and that's the keel. The keel is arguably the most critical structural component of a ship. Everything from the girders to struts to the skin of the ship is either directly or indirectly connected to the keel. The keel forms the basis of the draft, which will be the deepest part of the ship, as well as the overall curvature from stem to stern. All right, the next 2 terms we're going to go over are the molded baseline and the baseline at the bottom of the keel. The molded baseline is number 6 here, and number 7 is the baseline at the bottom of the keel. Now the keel on some ships, relatively small ones, might be very small, maybe only a foot, maybe 2 feet. So the distance in between the molded baseline and the baseline at the bottom of the keel might not be very significant. However, when you get into larger naval ships, such as the LHDs or aircraft carriers, this keel can be enormous. And so the distance in between the molded baseline and the baseline at the bottom of the keel can be significant. All right, so moving on from that, we have molded depth. Molded depth is number 8, which is right here. Now this dotted line goes from point D, which is the point where the deck edge comes, And the molded depth goes all the way to the molded baseline. Now here's a different reference point, so we're not using the baseline at the bottom of the keel, we're using the molded baseline. And we're going all the way up to where the deck edge is. So you can take this as the height of the ship at the center line minus the camber, which is number 1, and that's going to be that top point. Or by definition, camber is 0 at the deck edge. So you just take that deck edge point all the way to the molded baseline, which is on the top of the keel, and that's going to be your molded depth. Next up, we have design draft. If you've ever stood next to a Navy ship or a Coast Guard vessel or a cargo ship on a pier, you probably noticed right at the waterline there's several different numbers. Those numbers tell you exactly how much ship there is underneath the waterline. When we talk about design draft, as we are right here, we're talking about the distance from the design waterline or the designer's waterline, and we're going all the way to the baseline at the bottom of the keel. So that's going to be our number 9, design draft. Goes from the design waterline all the way to the bottom of the keel. And this tells us exactly how much ship we have underneath of the water. That allows us to make calculations and do chart corrections and navigation, voyage planning, things like that, so that we don't hit anything when we're sailing and steaming along. Now, there are several different types of draft. You have standard draft, design draft, navigational draft, as well as different drafts that are located on a Plimsoll mark, which is something that we'll introduce in a later series. However, we're going to go over molded draft right now. Now, molded draft is number 10, and it's going to start at the same place as design draft, so it's going to start at the design waterline. However, it's not going to include the height of the keel. So 10, which is our molded draft, it's going to go from the design waterline all the way down to the molded baseline. Next up, we have molded breadth. A lot of people will call this the beam of the ship, but it's essentially just the extreme width of the ship. This is important for when you're going through a canal or going through any place where you might have a restricted passage. So 11 here is 1/2 of the molded breadth. We start at the center line, and if we assume that everything is mirrored on the port side, then our entire molded breadth is going to be this distance times 2. And the last term that we're going to have on this diagram is something that's called dead rise, or rise of the floor. Now you see here, if you start the keel, most hulls are going to be very linear up to some point. If you continue that line all the way out, and you draw a point, here's B, where it intersects with the 1/2 molded breadth of the ship, that's going to be what's called your dead rise. Number 12 here goes from B to C. And it basically tells you if you don't have a lot of dead rise, then you have a very blocky ship. You're going to have a higher block coefficient than something that has a higher dead rise. And block coefficient is something we're going to get here later in the video. However, just remember, more dead rise, so more distance from B to C, is you're going to have more of a V shape in that hull. These next two terms, tumble home and flare, have to do with the curvature of the sides of the hull before it reaches the deck edge. Now, tumble home is defined as this point D to this line E. Tumble home is how much the hull sides kind of cave in at the top as they rise up to the deck edge from the extreme width of the ship. Some vessels have a strong tumble home, which means it comes in very strongly from the extreme width, and some ships don't have any tumble home at all. The next term is flare, and flare is seen pretty much on every ship. There are a few exceptions. However, the common design of Navy warships, Coast Guard ships have a flare, and flare is the outward curvature of the hull, especially seen towards the bow. All right, next up, we're going to get into the very basic terms of inclination. We're going to start off with longitudinal inclination. This is where we're looking at the side of the ship. So this diagram here, with the stern here and the bow to the right, we have two terms. We have trim and drag. Trim is something that's an instantaneous change in the drafts, and drag is something that's designed. Now, when I say change in drafts, remember when I talked about design draft and molded draft and all that? Well, the ship is going to have different drafts forward and aft. We refer to the forward draft as the forward draft and the aft draft as the aft draft. That's going to tell us how much ship is below that exact point on the aft and the forward side. You might also have some in the middle, which can give you your mean draft. And that's just an average between the two. So trim, you'll have 1 foot of trim by the bow, which means that the bow is 1 foot deeper than the stern is, how it's designed to be. Or you could have, say, 2 feet of trim by the stern, which means that your stern would be sunk down 2 feet deeper than the bow. A lot of ships are designed to have 0 drag, and drag is a designed trim. This can make your propulsion plant more effective, or it might help the hydrodynamics of your hull. So if you have a ship with 0 drag, and your trim gives you a foot, let's say a foot of trim by the bow, your bow is going to be deeper. So if you say trim by the head or the stern, that means that the head or the stern is going to be deeper than the other end of the boat. All right, lastly on the board, if you look to the left, we have these 3 terms. Where previously we talked about longitudinal inclination, we're going to talk about transverse inclination. We've already covered that a little bit in the first 3 lessons. Here we have the typical diagram that I've shown you before of a ship that's inclined over to some angle. Well, if you look at this ship and you don't know anything about it except you just have this hull that's over to the side, you don't know what's causing this inclination over to the side. It could just be the motion of the waves that are hitting the hull constantly every couple of seconds. That could be causing it, which means there's no need to worry. It happens all the time. The ship is just going to pop right back up. It could be caused by a heeling moment. So that's something like a strong wind off to the beam, or if you throw the rudder over really hard. If you've been in a high-speed turn situation, you know that the ship is going to roll to one side and then eventually to the other side. Or it could be caused by a list, which means there's an off-center weight that you've put, or you could have a negative metacentric height. So just by looking at this diagram, you don't know anything about what's causing the ship to be inclined. You could be in just a regular, everyday situation, like a roll. You could be in a more serious situation, like a heel. Or you could be in something that you've done or you've calculated that you're comfortable with, which would be a list. Or you might not be comfortable with it. Like I said, list is something that's permanent. And when I say permanent, it has to do with the weight distribution on board, or the location of the center of gravity with regards to the metacenter. And we'll get into that later, but that is the metacentric height. And it's a very important figure for commanding officers to know instantaneously how the stability of their ship is doing. So list is something permanent, so something caused internally. Heel, we call semi-permanent. If I have a heel caused by throwing the rudder over at a high speed, as long as I have that rudder over, the ship is going to be inclined. However, if I take that force away, if I take the torque away, then the ship is just going to right itself to where it was before the heeling motion started. So a heel is a semi-permanent. As long as that force stays with you, then you're going to be inclined to such and such an angle. And a roll is something temporary. It's just caused by the undulating of the waves hitting the hull and just making you go from port to starboard and to port again, that everyone has seen if they've served on any ship. All right, so now before moving on, I want to talk about displacement and tonnage. If you serve on a ship, you probably have a general interest in ships. And so you might read articles on G-Captain or Wikipedia or something like that, and you might see these 2 terms, displacement and tonnage, thrown around a little bit. There's a very distinct difference between displacement and tonnage, which I'm going to go over quickly right now. Displacement always refers to a weight. and that's always in long tons. We'll see light ship displacement, which we'll use a lot when we're talking about center of gravity. There will be full load, there's a standard displacement, as well as an instantaneous displacement. We'll typically be using light ship displacement, full load displacement, and instantaneous displacement, which should be between the two. Tonnage, on the other hand, is a measure of volume, typically. There is a deadweight tonnage, which tells you how much weight a cargo ship can hold until it sinks its limiting draft marks, which means that's the maximum amount of load that a cargo ship can take on. However, when you talk about gross tonnage, net tonnage, gross register tonnage, and net register tonnage, those are always going to be a measure of volume. Now, net register tonnage and gross register tonnage are terms that aren't used too much anymore. They were antiquated in 1994. However, gross tonnage and net tonnage are terms that are used right now, and they're typically used for tax purposes, trying to figure out how much a ship or a company should pay when they try and go through the Panama Canal, or a scenario like that. Gross and net tonnage are unitless numbers. If you are interested in that, even though we're not going to be using it in the course, you can look it up on Wikipedia or anything else. You can see the formulas on how gross and net tonnage are calculated. Gross register tonnage is the total amount of volume in a ship, and this is measured in register tons. And then net register tonnage is the amount of register tons of cargo carrying capacity in a ship. So that would be your gross tonnage minus the volume of the bridge, the volume of engineering compartments, volume of deck berthing or of crew berthing compartments, and anything that you can't put cargo in. So that's the difference between displacement and tonnage. All right, now we finally come to the last part of this diagram, which is going to go over some coefficients. Now, there are tons of coefficients that can be used in naval architecture, each one telling a naval architect something different that he can't get from any other coefficients. While we're not going to get too complex in what we're going to go through this lesson or this entire course, I do want to introduce these two because they will pop up later when we talk about statical curves of stability and how we define them, or actually how we derive them and where all these numbers come from. So here is the block coefficient. This is capital V with the little horizontal bar through it like I did in the last lesson, which is the total submerged volume of the vessel divided by the length, breadth, and depth of a rectangle that encompasses the entire submerged volume. So if you take the submerged volume and just picture it as a separate shape, if you make a rectangle that has the most extreme width, the most extreme length, and the most extreme depth in that submerged volume, then that is going to give you this rectangle that is your denominator in this case, length, breadth, and depth. Now you see how much of this rectangle is taken up by my ship's hull. The block coefficient gets its name because you want to see how blocky the hull is. If you have a coefficient that is closer to 1, this number will always be either 1 or less than 1. If you have something that's close to 1, so say a barge that's almost completely rectangular, then it's going to take up most of this block. However, if you have something different and you have a block coefficient around 0.6, then you have a much faster hull and something that's not meant to necessarily hold a lot of weight, but it's meant to go through the water really quick. Now let's take a look at the two different views that we can have on this block coefficient. So block coefficient is just a number, like I said, less than 1. However, if we look at the physical meaning of the block coefficient, here's a side view. It doesn't really tell us a whole lot, especially from a naval architecture standpoint, with what we need in this course. However, when we go from a top down, we're going to get what's called the waterline coefficient, and we see that here on the right side. This is extremely important to naval architects and even to someone like us just trying to get an understanding of ship stability. Ship stability and the determination of the metacenter and metacentric height and a lot of different things come directly from the area of the waterline or the area of the waterline plane. So what is this waterline coefficient that I mentioned? A waterline is just the area of the waterline plane. If you imagine a hull, so an entire boat, And if you cut a slice of it, a cross section, where the waterline meets the hull, and you take that and count it as just a regular shape, it's going to have like an arrowhead kind of shape, as you can kind of imagine. And then you divide that entire area by the length and the breadth of a rectangle that, just like the same concept over here with the block coefficient, that takes up the entirety of the length and the entirety of the breadth. And we're talking about just that cross section, not the entire submerged volume. So now this, you can get values from 0.45 to 0.8, depending on, again, how rectangular, how blocky that waterline area is. The next lesson, which is going to be lesson 5 in chapter 0, is just going to be a quick summary on what we've gone through here in lessons 1 to 4, as well as some practice problems that are really going to help show these concepts that we've gone through when it comes to center of gravity, center of buoyancy, and everything else. Hopefully it's going to tie it all together, and you'll come back and watch that lesson. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.